You ever just stop and think about how this all works? I mean, all the countless devices we use every single day, your phone, your laptop, some random server halfway across the world, how do they all manage to talk to each other so perfectly? It really does feel like magic, right? Well, it's not magic. It's actually a fascinating story about rules, a big fight, and a really, really weird outcome.
And that's really the big question we're tackling today. How can a device made by Apple just connect to a network and start talking to a server built by Microsoft, which is also talking to some gadget that's running on Google's software? I mean, these are totally different companies with totally different designs, and yet somehow they all speak the same universal digital language. How is that even possible?
To get to the bottom of that, we first got to appreciate the amazing world of connections we're living in right now. A world that, let's be honest, most of us completely take for granted. I mean, seriously, think about it. You can zap a photo from an iPhone to an Android phone without a second thought. Or you can pull up a website that's running on a Linux server using your Windows computer. We do this stuff all day, every day. It feels so normal. But trust me, not that long ago, this was pure science fiction. It was literally impossible.
So let's jump in the time machine and go way back to an era that I like to call the Great Disconnect. This is where you'll see the massive problem that had to be solved.
So, back in the 60s, some very smart people had this wild idea. What if we could get computers to talk to each other? By 1969, that idea became ARPANET, the granddaddy of all networks. And that idea? It spread like wildfire. Soon you had huge companies like IBM building their own networks for their own machines. But here's the catch. They were all proprietary. And that created a huge, huge problem. IBM's network had its own special language. Other companies, they had their own special languages too. They were like these digital islands that couldn't communicate with each other at all. It was basically a digital Tower of Babel. Everyone was talking, but nobody could understand a word anyone else was saying. And you gotta understand how deep this incompatibility went. We're talking about a time before things like Ethernet cables were standard. No, each company had its own plugs, its own special wires, its own set of rules. It was exactly like trying to jam an old Android cable into an iPhone today. It just doesn't work.
So after a while, everyone kind of realized how silly this was. If they wanted to build a truly connected world, they had to agree on one set of rules, a common language that every single device could understand. And the solution they came up with was something called a networking model. Just think of it like a blueprint. It's a whole set of rules and guidelines that spells out exactly how computers are supposed to communicate, from the physical plugs all the way up to the software. This way, any company, Apple, Microsoft, doesn't matter who, could build a device and know for sure that it would work with everyone else's.
Of course, it was never going to be that easy. This whole process involved tons of meetings, endless committees, and probably a lot of arguments. And after all that back and forth, two major competing models for how the internet should be built fought their way to the top.
And that's what kicked off what I call the War of the Models. This was a full-on battle to decide which blueprint would be the blueprint for the future of all networking.
Okay, and this is where the story gets really weird. Because as one expert put it, we ended up in this strange situation with two models. There's the one we actually use to run the entire internet, and then there's the one that lost the war. But for some reason, we still cling to it and talk about it all the time.
All right, so the practical winner, the model you and I are using this very second, is called TCP/IP. Now, to make the ridiculously complex job of sending data across a network manageable, it breaks everything down into layers, and each one of these layers has a very specific job to do.
And that's the key right there, the layers. This system makes everything so much simpler. You've got the physical layer, which just worries about the actual cables and electrical signals. Then you've got the network layer, which is all about IP addresses and figuring out how to get your data across the internet. Each layer does its job, then just hands the data off to the next layer in line. It's brilliant. So what about the loser in this war? Well, that was the OSI model. Now, if you look at them side by side, you'll see the bottom layers are pretty similar, but the OSI model is way more granular, more detailed. It splits the top part into three separate layers: application, presentation, and session, while TCP/IP just lumps all that stuff into one big application layer.
So you're probably thinking, okay, if TCP/IP won and it's what we actually use, why on earth are we even talking about this 7-layer OSI thing? And that, my friends, is the great paradox of modern networking. The answer really just boils down to history and old habits. Back when the War of the Models was raging, everybody was betting on OSI.
I mean, it was the favorite. It was this beautiful, detailed 7-layer masterpiece. So what happened? Universities started teaching it. All the textbooks were written about it. And pretty soon, every network engineer on the planet was using its language, its layer numbers. It just became the default way to talk about this stuff.
And his quote just perfectly captures how sticky an idea can be. Even after TCP/IP was the clear winner in the real world, or, as one expert so dramatically put it, after it killed and murdered OSI, the language stuck around. Engineers just kept on referring to the OSI layers because, well, that's what everybody knew.
In fact, the OSI model is so deeply burned into the culture that network engineers to this day still memorize its 7 layers. There's a famous mnemonic device for it, going from the top down. All people seem to need data processing. That's for application, presentation, session, transport, network, data link, and physical.
Okay, quiz time. Let's put that to the test. Which one of these common networking gadgets operates mainly at layer 2, that's the data link layer of the OSI model? Take a second and look at the options on your screen.
And the answer is the switch. If you said switch, you are spot on. A switch is a classic layer 2 device because it uses MAC addresses, which are part of the data link layer, to smartly send information to the right device on a local network. A router, on the other hand, works at layer 3 with IP addresses. And a simple old hub, that's just a dumb layer 1 device that repeats signals.
This legacy is absolutely everywhere. To this day, if an engineer is trying to fix a problem with, say, your web browser, they won't say it's an application layer issue based on the TCP/IP model. Nope. They will almost always call it a layer 7 issue, a direct reference to the OSI model that technically lost the war. So there you have it. We've got this practical model that we actually use, and this theoretical model that we talk about. And together, they make up the great digital handshake that connects our entire world. So the next time you're streaming a movie or firing off an email, see if you can picture it, that little packet of data making its journey down through the layers on your device and then back up through the layers on a server somewhere, all thanks to a war that one model won and the other one, somehow, never really lost.